Hello, all. A very good day. I hope everyone is safe. So, this is the third part of implementing our unsupervised representation learning. Here, we are trying to implement the RotNet, and the idea is that we are trying to emulate the scenario where we have small amount of label data and a good amount of unlabeled data. So, how we can use unsupervised representation learning to make use of this unlabeled data. And in the previous video, we created a data loader. So the data loader object will give us the samples and their corresponding labels for both supervised and the self-supervised task. So for the supervised learning task, where we have label data and we know its actual labels, it will give us the image or the samples along with its labels. So here, as we know the labels, 0 is daisy, 1 is dandelion, 2 is rose, and so on. But at the same time, we also created a data loader for the unlabeled data by creating a proxy task, where the proxy task is the rotation. So we took an image and simply rotated it by 90, 180, 270 and created a proxy label where 0 is the 0 degree, 1 is the 90 degree, 2 is the 180 degree, 3 is the 270 degree, and we'll use this for doing our self-supervised learning. So in this video, we are going to use those data loader, and we are going to train couple of models like supervised models, self-supervised model, then use the knowledge of the self-supervised model for tuning the supervised model. And then we'll see how this simple approach of doing unsupervised learning can help us improve performance by using just small amount of label data. So let's get started. So, if you remember, we had three folders of dataset, or we distributed our dataset into three sections. So, one was this, flower recognition trained dataset, around 4023 samples. And then another was this, obviously, this test set, uh, which is kept, totally separate just for testing the model. Then we also created a small amount of label data by taking 10% of this train set. So what we'll be doing, we'll be using only this one for training as a small label data, and this one, this flower recognition train, will be using as an unlabeled data. Will not be using their labels. We'll be using as unlabeled data to do the self-supervised pre-training. Okay. So how it will look like? So for the first stage, we'll have this small label data of 400 samples, and this is the actual labels, and we'll be doing the supervised training for the task of flower classification, which is our actual task. And then we'll do this. We'll see the performance, and then we'll do the self-supervised learning, where we'll have this flower recognition train, that 4000 samples. We'll treat that as unlabeled data, and then we'll create a proxy task of rotation. This will be a proxy task, and we'll do self-supervised training for the task of rotation classification. Now what we'll do, whatever knowledge is gained from this good amount of unlabeled data, we have to make use of it. So we will simply use this model, like this pre-trained model, and then get rid of the last layers, add the nodes as per the number of flowers, because here we'll be doing the actual task of flower recognition, and then fine tune this model, this pre-trained model, on this small label data set, and then again see the performance of it. Okay. So yeah, basically with this, we're making use of this unlabeled data to gain some knowledge, so that we already have a good pre-trained model, and in that case, just by using small label data also we can get good performance. So that's the whole idea, and the final evaluation will look something like this. So we had this model, this model which is trained on small label data but without any pre-training, and this model which is trained on again on small label data but with pre-training based on RotationNet. So we'll compare these two models. So basically these are the two models, and then if you remember, we have a separate test set. So we will compute the performance of the test set on both this model, one without unsupervised pretrain and one with unsupervised pretrain, and then we'll compare the result. So the codes are there, and basically before jumping to the code, I will just explain the layout. So we will have this main function, And in this main function, we are just going to call the config.yml file. So if you remember, there is a config file that we are using to define all our parameters, paths, etc. Now this config file will call this function called train and evaluate. Now this train and evaluate function, what it will do, it will load the model, it will load the data loader, it will define the optimizer, it will define your experiment directory, the tensor board writer, and then for every epoch, it will call the train function, this train function. Okay, and this train function, for every epoch, it will train the model, it will log all the losses and accuracies to the tensor board, and then at the end, it will return back the train loss and train accuracy. Okay, and then again we'll call the validation function. Now this validation function and test function resides in a separate script called evaluate.py, but here from the main script, train and evaluate function, this validate function will be called. It will do, run on the validation data, and then it will return validation loss and validation accuracy. And then we'll save the checkpoints and the best checkpoints based on the validation loss. And for the best checkpoint, then we will compute the result on the test data. So that's how the whole code structure will look like. We'll have a main function with where we just need to call the config file, and then this config file will be passed to the train and evaluate function, which will be loading the model, loading the data loader, defining all your optimizers, tensor board, and then for every epoch it will call a train function which will do the training, return the loss accuracy. It will call the validate function which will do the validation, return the loss and accuracy, and then we'll save the checkpoints, and for the best checkpoint we do the test. So let's jump to the code. So I hope you remember this folder or directory architecture. So we discussed it. So for the data loader, we use some of the helper function, and even for training, we'll use some more helper functions. So let me discuss that with you. So yeah, so this is one helper function of saving checkpoint. So we will just pass the state or the state of the model, and then we'll see if it's the best checkpoint. Then we'll have save path, and then the name of the checkpoint, and then we'll simply, whatever the save path is there, we'll simply save the checkpoint, and if it's a best copy, we'll save it in the name of best. And then we can load the checkpoint as well. So simply this will check if there is a path to the checkpoint, or else it will raise an exception error. And then map location will map it to the device that you are trying to load. Either here I've mentioned default CUDA, it could be CPU as well. And okay, there were two methods. So basically many people save the checkpoints by giving a keyword of state dict, or many people they save it directly as a checkpoint. So this is just to denote that. And yeah, if you are saving the optimizer state as well, so which I'm doing, which I'm not doing, but if you're using it, then also you can load it. Then there is this logger function. So this logger function will help us to log all our information. So log file will look something like this, where we can, whatever information that we want to log in, like the state or the result, like right here I'm logging just the result after every epoch, and the learning rates if I was using a varying learning rate. For this experiment I'm not using, but yeah, and you can log many such values that you want to. So this helper function will do that. And now there is one more thing, that this helper function will also help you to print, like instead of just writing print, you can just write logging.info and it will print on the console as well. So this function is used to do that. Yeah, so these are the two new helper function. This I think we discussed last time. Then there is this metric. So we'll call this running average, and this class, what it does, it will take samples, and then it will compute a running average of it. So this will help us to compute the average loss over different iteration, different epochs, or the accuracy over different iteration, different epoch. Now there is a function to compute the accuracy. So this one I'm not using. This you can use it. I'm just using in the train script only, just simply making the prediction and target equal and computing the accuracy. But you can do it here. This function I don't remember from where I copied it, but yeah, it does this. It can calculate the max top 5, top 1 accuracies as well. So yeah, these were some helper function. Now let's go to the train script. So if you remember the layout that I just showed, how the main function, so we'll call the train. So this is the main function. So here what you have to do is simply define and call your config file, and all the config file resides here. So config supervised learning.yml, and then there is a utils, this utils, it will load the YML, and then it will call the train and evaluate by passing this config file. Now what happens in this train and evaluate, we'll see here. But let's first see the config file. This is the config as supervised learning YML file. So you can define the number of classes. It's a supervised learning. There are 5 flowers. You can define the mean, and I think we discussed this in the previous video. Then we need to define the data path. Then we can define, what kind of experiment it is. Is it supervised or self-supervised? Because we are storing all the experiment in different section. And then you can give the directory name. So supervised learning without pre-training experiment 1. Then the log file name. Then here we are not using any pretext task because we are using supervised learning, not self-supervised learning. So we'll make it false. And there is an option to even use pre-trained model. So we need to give the path, of the pre-trained model. Here I'm giving the SSL pre-trained model, the self-supervised pre-trained model that we'll do for the 3rd experiment. And then you'll give the network, the momentum, learning rate, the optimizer, and then batch size, the validation split, and etc. And how after how many epochs you want to save the weights. So you can configure it as per your requirement as well. Now let's come back to the training thing. So now we'll call this train and evaluate with this config, and this will create an experiment directory by using the save directory path that you have defined. So like the name of the experiment, say supervised learning linear probe, or whatever experiment you give, will create a directory and it will store all the information of the experiment there. So if it's not, it will create it. Now I will create a logger, logger handle here by calling that utils function set logger, and we need not print here. By just doing logging.info, it will log into the log file as well as it will print here on the console. And then I'm giving the option of using CUDA. Again, it's taken from the config file. If CUDA is available and you're giving any specific CUDA number, like you want to use GPU 123, you can give it here. And then based on that, the device will be selected, either it's CUDA or the CPU. And then this is the logs, the tensor board logs that I'm creating. So here, actually you can do it in 2 ways. Either you save the logs hard-coded inside that experiment directory, or you save outside the log and outside of any specific experiment directory, and you keep logging the different experiments. So what I'm trying to say is you can do in 2 ways. So one is this way. If you see, so I have one TensorBoard log where I'm logging all the experiments. So this becomes easier to see various experiments when we have to compare how different experiments are performing. So this is, say, without pre-training, and this is with just fine-tuning last layer, then this is fine-tuning more layers, so we can compare it. So I'm doing in that way for the supervised model. But if you are doing some independent experiment and you don't want this comparative, you want just this single curve for a single experiment, then you can simply put that inside this experiment directory. It will just simply reside inside this experiment directory folder. But nonetheless, I am doing this. So I am having this TensorBoard supervised and demo, and inside this everything will be. Then this is the name of the log. So RotNet pre-train. I'll just name it RotNet without pre-train. Without pre-train. And then once the writer file is defined, this is for the TensorBoard logging. Then we'll call the data loader. If you remember, we have created this data loader. So this is the data loader, and in the init, so you need not call this specific function because in the init itself, I have defined that I'm inputting get data loaders, get dataset. So I can simply call from the module name itself. So that's why if you see here, I'm simply calling this module data loaders and data loaders dot get data loader function, and I'm just passing this config file, and then you will get the data loader train, data loader well, and data loader test. So for us, we did not have a validation set. That's why in the config file, if I can show you, I have defined that take a validation split. So of 15%. So it will simply from the trained data create a 15% for the validation data. Then I'm calling the model. So I'm using this off the self ResNet 18 and it resides in this models module. So model is simply getting this ResNet 18 and yeah, and this is basically if you because I'm using from the torch vision, so they have the option that you can use the ImageNet pretrain, but I'm not calling that. I don't want the ImageNet pretrain. We are doing everything from scratch. So yeah, this will call this model, and then the last layer it will then define as per our number of classes. If it's for supervised learning, there are 5 flowers, so it will be 5 classes, and if it's for self-supervised, there are 4 rotation, it will be 4 classes. So this will call the model. And yeah, this section is basically for loading the pre-trained checkpoints. So if you have stop experiment for 50 epochs and you want to start after 50 epochs, so you can use this flag, and then you can in the config file you can give the path, and then we'll load it and then start training from there. And there is another option of using the self-supervised pre-trained. Okay, so we will also do this unsupervised pre-training. So that pre-trained model we can load here, and then we can define which of the layers we want to keep, which of the layers we want to fine tune. So this we'll see later when we come to doing the self-supervised based fine tuning. Right now we are doing this simple supervised one. So but it's good to know that there is an option of using the pre-trained model or the self-supervised pre-trained model. So I'll come to this later. Then we put this model to the device, whichever CUDA device you want to run it. And this is basically just for creating the graph in the tensor board. And then this is defining the optimizer. Then scheduler, you can define any learning rate scheduler. So I'm for this experimentation, I'm not using. One example I've given is to use multi-step LR, but you can use any other like cyclic or any other scheduler. Then we define the loss function, cross entropy, and yeah, this I'm defining a iteration count just to create a graph. Sorry, create this one. Like we'll have logging for every epoch, but we can also have logging for every batch or every iteration. So for that, yeah, now what we do simply we'll run this for as many number of epochs. Now for every epoch we'll call the train function by passing the model, the device, whether CUDA or CPU, the data loader, the optimizer, the loss function, the experiment directory, the writer, and the train function is here. Yeah, so it will simply create a progress bar with the TQDM. Then it will create two objects, one for loss and one for accuracy, to keep a running average. And this is basically to compute how many correct prediction and total prediction, so that we can compute the accuracy. And then I'll call model.train, and then for yeah, this I should make it for the full data loader and not for the slice of just 10 samples. Like I discussed in the last video, iSlice is used to just slice out from entire data loader just as many batches we want. So we'll simply then get the data and the label, we'll move them to the devices, then get the prediction, get the loss, then get the the probability score and the predicted class, and then we'll compute the number of correct predictions and then the total, and then compute the accuracy as correct by total. And then we'll pass this to a running average, which computes the running average to get an average of accuracy, average of loss, and then this loss and the accuracy will pass it to the tensor board writer, so that we can visualize in the tensor board. And then we'll zero the gradient, we'll do a back propagation, and then we'll do a step optimizer step, and then we'll update the progress bar. And if there is a scheduler, then we'll run that scheduler step, so it will change the learning rate. Then we'll see if we are using the varying learning rate, we can also log those learning rate here. So here is mainly again logging to the tensor board after every epoch, and this was after every iteration, every batch, and then final logging in the file as to what was the result after the training of the epoch, and this will return the loss and the accuracy. Now we'll come back here, and then we will call the validation function. Now it does the same thing. and it will return the validation loss, validation accuracy, and then we'll see if there is improvement in the validation loss from the previous, and if, then we'll consider this as a best loss. And then if it's a best loss, or if we have given a config that after how many steps we need to save the checkpoints, we'll simply call the save checkpoint, and the checkpoints would be saved in the experiment directory that we have defined. And then we'll close the writer. And once the training is complete after every epoch, then we simply load the best checkpoint. And on the best checkpoint, then we compute the performance of the test data. And then we log this test result. And then at the end, when we are done with every training, we'll simply save this config file so that we know which configuration. So this is the experiments, if you see, and this is the experiment name. So we should know which config file was used to generate this experiment. So it will be saved here, like, so that we can further see and know what was the config file. So this is the whole training structure for the supervised learning. And for the self-supervised learning, this is pretty much the same, just that train SSL RotNet, here we'll be calling the self-supervised YML file. And again, in the self-supervised config, where is it? Yeah, self-supervised config YML, we will be defining the pretext task. Here we are using rotation. Maybe in future we can use some other pretext task as well. And then we define number of rotations. And then I think remaining all will remain same, because self-supervised learning is also kind of supervised learning, just that we are having a proxy labels. Again, like the supervised learning, you can configure the config file, and everything else, I think it's pretty much the same. You have this train and evaluate function that create this directory. Then we have this data loader. Now the data loader would be having the rotation labels. Then you have this optimizer, scheduler, calling the training, saving the checkpoints, and the same thing for even train SSL. Okay, so this covers the first two things that we discussed. Okay, we did a supervised training, we did a self-supervised training. Now we have to make use of this self-supervised pre-trained model. Okay, and then do your fine tuning on this and see if it improves or not. So yeah, let's see how we can do that. So once we have done our self-supervised pre-training, let's see how we can make use of it. So our self-supervised pre-training model is, the script is this, and the model is ResNet 18 with the number of classes being 4, as there are 4 rotations. So how can we use this pre-trained model, which was trained on nearly 4,000 unlabeled samples, and fine-tune it for a very small, like 400 label samples, for our actual task of flower recognition. So for that, let me switch to this slide, because I wanted to show something. So I'll make this, and then I'll choose a pen. So this is our ResNet 18 model. So basically it is divided, it's structured in this layer 1, layer 2, layer 3, layer 4, and every layer has blocks, and then blocks will have conv layers like this. So basic block will have this kind of architecture, 2 conv blocks, and bottleneck block will have 3. So ResNet 18, the model which I am using, is using basic block. Okay, and it's organized in layers format. So this one block is layer 1, layer 2, layer 3, layer 4, then average pool, and then a fully connected layer, like which is 4 because of the number of rotations. So once we have done this pre-training, let's see how we can use it. So what we can do is we can just fine-tune the last layer. I mean, use this entire block as a feature extractor, and then just fine-tune this last layer. Now instead of 4, there will be 5 classes, because there are 5 classes of flowers. And then we can do the fine-tuning of this layer using this as a feature extractor, and I'll name this experiment as RotNet pre-train fine-tune 1. And what I observed was the result of this this fine-tuning was worse than the model without RotNet pre-training, and I'll come to this as why, but let's move ahead. So this is one experiment I did. The next is that you use instead of using I mean the last layer 4 as a feature extractor, you further move up and fine-tune even the conv layers, like the last layer and the conv layers, and use the feature extractor as after the layer 3. So in this, I saw that, okay, this was better than the model without RotNet pre-training. And this experiment, I named it as RotNet pre-trained fine-tune 2. So actually it was better than the previous one, but it was still not better than, the model without RotNet pre-training. Then I moved, one layer above, and instead of fine-tuning just, two con block, I further fine-tune 4 con blocks and a fully connected layer. This will be 5. And here I use this 2 blocks as feature extracted. And here I found that this was the best performing model. The results were much better than the model without RotNet pre-training. And this experiment was called RotNet pre-train fine-tune 3. And then I thought maybe let's move even further. The next experiment what I did was just that we use only this layer 1 as feature extractor and fine tune, this 3 layers of conv and then a fully connected layer. So this was better than the model without RotNet pre-training, but it was not better than the previous experiment. So we'll see the reason, and this also comply with the author's result. So what they found, they also did experiment with number of con blocks, and they found that if they were using the feature extractor after second con block, the result was best. And the reason was because if we use features after this like more deeper conv layers, then those deeper conv layers or the or even say the last layer, they are basically more specific to the task of rotation and not for the flower classification. So that's why they are performing not that much great. But if we use this, after second con block as feature extractor, they were more generic feature, and then fine tuning the later layer for the task of flower classification, it was performing better. And the reason why, in the previous experiment, if we just use layer 1 as feature extractor, like if you fine tune everything, then this was not better than using up to feature extractor up to second block, was because the amount of data that we have for fine tuning is not that much. So here the features were already quite generic, and only the later layers, they were very specific to the RotNet. So if we have more data, then we can fine tune even this. But if not, then I think after second con block, this was performing good. So depending on the model you choose, then you have to actually experiment and see which one is giving best for you. But for me, this was the case. Now let's see the code, how we can code it out and experiment it. So I'm not doing training here in this video because it's going to take a lot of time. So I'm just going to explain it, and it's the code will be there. It's pretty much simple. You can run the training. So this is the training logs, and this is the validation log. So let's look on the validation log first. So this is the accuracy and this is the loss. So this is the model without any pre-training. So then I will do a RotNet pre-train fine-tune 1. That is just fine-tuning the last layer, the classifier layer. And I see that the accuracy is bad. The loss is also bad. Now I do another experiment that I fine-tune this the last con layer as well. So that was RotNet pre-train fine-tune 2. And here I see it's better than the just fine-tuning the classifier layer, but still not better than the without pre-trained model. So when we come to the third RotNet fine-tune 3, where we are fine-tuning this layer 3, layer 4 and the last layer, then we see, let me run this, that the performance of the model has improved. If I just get rid of this, so this orange one is without pre-training and the blue one is with RotNet pre-training, and you can see the improvement. And even if I do further take another layer, so this is better than the without pre-train, but still not better than the previous experiment where we are just taking the feature extractor after the second con block or after layer 2. So this was my experiment. So this was giving the best RotNet pre-train fine-tune 3. And yeah, that you can also try, and let's see how we can do it in the code. So you have to do simply, you have to go to your config SL, and you have to make your use SSL self-supervised learning as true. You have to give the path of where your checkpoints would be. So for me it is in SSL RotNet, and the best checkpoint for me was this. So you can see which one is best for you, and the other training parameters you can define the fine tuning parameters. Then we'll go to this train supervised learning model, and here let's see this part where we define this fine tuning. So here in the where's the right? Yeah, so here you can change the experiment name as RotNet pretrain fine tune 1, and then when you do the next, fine tune 2, fine tune 3, and so on, and everything would be in your TensorBoard supervised demo. And then simply you can run that using this command, like go to that path where your TensorBoard is, TensorBoard -- log directory, TensorBoard supervised port number, and you will get the logs like the one you see on the screen. Okay, so yeah, here we'll give the logs that where we want to store, and in the config SL we'll give the path where we want to save the training results. So SL RotNet pre-trained 1 for me. And so this part is interesting. So what we'll do here is we will simply define this SSL experiment directory, and then we'll load this checkpoint using torch.load. And then, so for me, the way I saved, so if you see the way I saved the checkpoints was like three things: the epoch, the state dict, and the optimizer dict. So state dict is the checkpoint, so I'm just loading the checkpoint using this. Okay, and then what I'll do, if I'm doing this fine tuning of just last layer, then I will just comment these things out. I'll be just deleting the last layer, the if I go here, this FC layer, the weights and biases of this, I will delete those checkpoints, and then I'll keep the pre-trained checkpoint of the previous layers, and then I'm going to load that in the model. So I will do this now. So this will delete the last checkpoints, the weights of that, and then I load this to my model. Okay, so it says it's missing key because we have deleted it, but that's fine, it is still loaded it. Now what you have to do is you have to freeze this. So if you remember this RotNet, so you will freeze this all layers except this layer. So that's where I'm defining for name parameter model dot name parameters. So I'm just going to freeze this FC. So if there is FC in the name, so I'll just do in name, sorry, and then I'll comment this for now. Then it will make the requires gradient as true, else it will make it as false. So this will freeze out all the layers, and then it's basically the same way of doing the training. Now suppose you want to do you also want to do this one, say RotNet pretrain fine tune 2. Sorry, I'm blabbering a lot. So here you want to keep we want to fine tune this weights, sorry, the layer 4 weights, and as well as the FC4. Okay, so what we'll do is we will simply uncomment this. So in the layer 4, there are conf. So if you see the code, there are two blocks: basic block 1, basic block 2, and in each block there are two conf layers. So I can also show you if I just print the model, and you'll see in this is the last conf block. There is basic block, and there is conf 1 and conf 2, and then sorry, in the layer 4 there are two blocks: basic block 0, basic block 1, and each basic block there is conf, and then conf. So what we'll do, I'll do layer 4 dot 0 dot conf weight, layer 4 dot 0 dot conf 2 weight, and then layer 4 dot 1 dot conf 1 weight, and layer 4 dot 1 dot conf 2 weight. So I will even delete this pre-trained weights because I'm going to fine tune this one. And then here, instead of just doing if FC, I will also give it FC, and then I'll get rid of this. So layer 4.0.conf, layer 4.1.conf. So if that is in the name, it will take both conf1 and conf2. Then it will simply do that, it will make the required gradient is true. It means it will fine tune those layers, and the others it will make it false. And then similarly, if you want to replicate this third experiment where you are also, sorry, yeah, you are also, taking the layer 3 for fine tuning, then you have to just make this, uncomment this as well. And here you have to also include, the layer 3 name. Sorry. Oops, I did something. Okay, sorry for that. I will just uncomment this, and then yeah, so I'll have layer 3.0.conf. It will take both conf1 conf2 and layer 3.1.conf layer 4, and then it will make the gradient as false. So this is for the ResNet 18. If you use any other model, then you can just print out and you can see, which one you want to freeze. You can just access it and freeze it, and then you can do your training and you can see, which one is performing the best for you. So this was the training part. I will upload my checkpoints which I have done, but I think, yeah, it's better you just train yourself and see, experiment it. The code is there, and yeah, I think that will do for now. I think I've explained the things that are required to do the training and fine tuning. So that was all about, you need to understand about how you can train your supervised model, self-supervised model, and then do the fine tuning. And in the next video, we will do some evaluation. So we will, in the self-supervised learning part, we can evaluate by taking the features and training a simple linear classifier logistic regression and see which one is performing better. So we'll do that. We'll also do some visualization on the tensor board, and we'll see how it is. And one more point, so I realized this later that, for this data set, using this kind of self-supervised learning RotNet, it's not a good self-supervised model. So just think about it, in this flower data set, why this RotNet would not be a good technique. And in the next video, I'll discuss that why this RotNet is not good technique for this flowers data set. And that's why I will maybe experiment with dogs versus cats data set as well, where it will make much more sense. But think about it, and in the next video, I'll answer this question. So I hope this video was useful to you. And if it was useful, then please do give a like, share it to anyone who you think it will be useful to them. Comment, subscribe, and be safe. Till then, keep learning, keep exploring neurons. Bye. Namaste.